afternoon. My name's Joel Kirschman, and today we'll be talking about a new feature to the AWR design environment that effectively allows you to streamline your design. The presentation is about 50 slides, but I only have 15 minutes, so we're going to go at a quick clip here. If you've got any questions, obviously ask it at the end. So the process here, the outline of this presentation, is that we're going to do a first cut design of an RF link. We're going to make a refinement on that link by communicating with a circuit tool, and then we're going to replace one of the components with an actual commercial off-the-shelf product, and then we're going to pass a communication signal through this link. The beginning of the link, you define your RF band of interest using a GUI interface. Here I've defined my band, my RF input band. I can have multiple bands of interest if I choose, and I can also have interfering bands. Once you define your band, you can start populating this product with behavioral models. So if we look from left to right, you see I have a filter, an amplifier, a filter, and then a converter. The key parameters of these models are available to you in this diagram. As you're populating the diagram, you can see the spurs generated simultaneously as I enter components. So here I'm looking at the output of the mixer, the corresponding intermodulation products, and the IF frequency of interest here. And I can see a tabular format appear as well. The LO is at 100 megahertz, the input is at 1.1 gigahertz, my IF of interest is at 100 megahertz. Now we'll drop down a low-pass filter in the design. We can look at the resulting spectrum, the characteristics of that filter to isolate the 100 megahertz signal. The other option is we can say, let's have a 900 megahertz pass through this link along with the 1000 megahertz signal. We're letting the image go through. We can see the resulting interfering products as a result of the image. The last thing we can do with this quick look of this design is pass a signal at 1050 megahertz. That will produce a 50 megahertz signal, or half the IF. As a consequence of passing the 1050 megahertz signal, we can see we have a byproduct falling on the 100 megahertz signal of interest, and the tool will indicate to us it's a 2 minus 2 product. Continuing on with the design, the other part of this wizard allows you to do cascaded analysis. Here we're showing cascaded noise figure and cascaded P1 dB and gain of our link. We can do the same calculations in Excel spreadsheet, and we'll realize that the first cut of this design is giving us the same noise figure for the link. We want to take a further step, and we want to analyze this system and account for real-world effects. So we switched from a wizard tool that gave us instantaneous gratification of spur results, gave us the first cut results of noise figure, gain, and P1 dB according to standard equations. We create a system diagram with the push of a button, and we end up in the AWR design environment system tool called VSS, Visual System Simulator. The components are realized either as behavioral model, intermodulation products table for a mixer, or touchtone data for a filter. First cut design, instantaneous gratification, VSS. We can go further on and analyze this link, account for phase noise, account for things going into compression, and account for mismatch between components. We look at the spurious results from the previous tool, the planning tool. We compare the results to the system tool, and we see the byproducts are in close alignment. We're looking at the output of the mixer. The next thing we do is we put the low-pass filter. Once again, the output of the two tools are in alignment. There's slight discrepancies due to modeling. The model that's used in the RF planning tool for the amplifier is not one-for-one 100% compatible with that used in the VSS, so slight discrepancies can be seen. Simultaneously in VSS, Visual System Simulator tool, we're doing a noise figure calculation. Using the wizard, the first cut of the RF architect, we discovered that the noise figure was 4.38. Using an actual system tool that will account for noise at the image frequency, that will account for mismatch between components, we look at the resulting noise figure is not in agreement with the first analysis. So we have to go back to that system, analyze that architect a little further. So what we're going to do is look at the filter that was used to reject the noise at the image frequency. The filter that was rejecting the noise at the image frequency, 900 megahertz, in the actual design, in fact, doesn't have that great attenuation at 900 megahertz. So the 900 megahertz is passing through. The noise figure is altered as a result of having that noise at the image frequency pass through the mixer. So we'll take the first filter that we designed, make a further refinement, make the skirts steeper, reject more noise at 900 megahertz, do the analysis in VSS, and now we can come in alignment with the first calculation of noise figure. So going further with this, I'm going to skip this slide. This slide just is indicating to you that we can account for components going into mismatch in the calculation of noise figure as well. But we're going to concentrate on that filter. All I did was create a behavioral filter. I refined the characteristics of the behavior filter. The next thing is I have to implement this filter at a circuit level. So I went into the AWR design environment and used a synthesis tool that allows me to give the key characteristics of the filter. A schematic is generated automatically in this wizard. This schematic is transferred into our circuit tool called Microwave Office. Now the goal is to take this filter and replace the behavioral filter with an actual implementation in the circuit tool. So we went for a first cut design. Now we're going to another level, second, co-simulation with a circuit simulation tool. And I keep on pressing the wrong button here. And then we replaced that filter, which was represented by behavioral, which was represented by touchstone, with an actual implementation. We'll run the simulation again and look at the resulting noise figure. And now we see here that the resulting noise figure calculated is 4.46 dB. We can drop optimization goals at the system level. We can optimize on the skirts of this filter to reject the noise as well. So two tools communicating to each other, optimizing on key components in the circuit level vis-a-vis a measurement at the system level, noise figure. Moving on, now we're taking the next step into the process of our design. This design consists of behavioral models. Now we have a circuit-based model, but now we're completing our design by using data from a vendor part. So VSS can capture more information for an amplifier than just S parameters. We can count for gain, P1 dB, and noise figure along with the frequency dependency of these parameters. So some of the key measurements that you can make are frequency, temperature variation, noise figure. Here we're looking at frequency versus noise figure at one temperature, and then different frequencies, different temperatures, available gain, slight discrepancies in the outmost available gain. We're going to go back to that design, and we're going to replace the behavioral model of the amplifier. The first model of the amplifier was a fifth order polynomial simulating the nonlinearities. We're going to replace this model with a database model. Database meaning that it's going to reference a data file. You as a user accumulate this information, create a text file for the VSS model to understand. The text file consists of variables. So here's the temperature of 45 degrees, 25, or 85. I can't read that far. But for each temperature that I'm setting, I have a column of frequency, gain, P1 dB, and noise figure. I replace the fifth order polynomial with a database model, a vendor part, a commercial off-the-shelf component. I resimulate, and then I realize here that the noise figure changed to 4.64 dB, while the handheld calculations in the previous simulation resulted in a noise figure of 4.46 4.46 dB, so approximately 2.2 dB off. So why now are we 0.2 dB off in the calculation of the noise figure? Well, the behavioral model was replaced with a file-based model. We're no longer using the fifth order polynomial, but the amplifier is looking at data. And if we look at 900 megahertz, that's the image, we see here that the gain is 7.6 dB. So there was extra gain added at that image due to the frequency dependency of that amplifier. If I could switch this number to 5.8 dB, I would realize about 4.4 dB noise figure, but I can't. So what are we going to do? We're going to go back to that filter, and we're going to further optimize on the skirts to reject slightly more noise at the image frequency. So I have my optimization goal here, and here at my nominal temperature of 25 degrees C, I can get 4.39 dB of noise figure. So the steps were ideal, circuit-based model, commercial off-the-shelf component, getting closer to reality in our design. The next step is that we can do an analysis. Here we're doing frequency versus noise figure over temperature. A specific bandwidth has been defined. Each color indicates a different temperature, the characteristics of the filter that we're using. Now we move on to the next step. I make all my qualifications for spur analysis. My noise figure analysis is done. I could utilize VSS signals to stimulate the same link. And at this point, the metric is going to be different. The metric that we're going to be looking at is bit error rate. So VSS supports many different measurements. It has 2 simulation engines in it. Once I switch to a communication standard, not only does the frequency domain analysis continue, but now we can look at time domain measurements, such as receiver sensitivity or bit error rate, and eye diagrams and spectrums. So from concept to a closer hardware implementation, all achieved in one tool. I'll leave 3 minutes for questions. Any questions here? So I condensed 1 hour into 15 minutes. I hope you got the gist of it. If you want to learn more about it, you can come by the National Instruments booth and learn about our software. Thank you.